Welcome, Math 1100 students. This is the instruction for section 13.5. This section isn't actually any different from the others except that there's a couple of nice things that if you catch on to the pattern that you see here, it'll make things factor faster. But I'm going to explain it pretty much in the same way that I explained section 13.4. So to begin, we're talking about factoring perfect square trinomials and the difference of two squares. And we'll need to talk about what that is. So what we have here is what is called a perfect square trinomial, which means that your first term and your last term are both perfect squares, because x squared is the product of x times x, which we've talked about before. And 36 is the product of 6 times 6. And what this is going to let us do is it's going to let us kind of cut to the proper factors to achieve the middle term much more quickly. So when your first term and your last term are both perfect squares, one of the things that you should notice is that one possibility for the factors would be x times x for your first terms. And since this is positive and your middle term is positive, positive 6 times positive 6, because positive 6 times positive 6 will give us that positive 12. And so x plus 6 times x plus 6 is in fact x squared plus 6x plus 6x, and then of course 6 times 6 is 36. And it is those two in the middle that give us the positive 12x. So if you understand that what you're looking for is that the first term is a perfect square, and the last term and they have to both be perfect squares, then you might be able to find the ideal factor combination by taking the square root of both of those. Now the hitch comes in when the first term isn't x squared. So again, this method will still work that we've already learned. You don't really need a new method. The first step is still, is there a GCF? And that should still, even when you have a perfect square, be your first question. And the answer is no. So then your second step is to put your first term in your first box and your last term in your last box. And you're looking for a pair of terms that are factors of 36x squared. And since that's going to be x times x, we only need the factors of 36. And 36 is positive, and our middle term is positive, so that tells us both of the factors are going to be positive. And we know that it's 36 because this is 1x squared times 36, so it's 1 times 36. And so the factors are 1 and 36, 2 and 18, 3 and 12, 4 and 9, 5 doesn't work, and 6 and 6. And you're looking for a sum of 12. Well, 1 plus 36 is 37. 2 plus 18 is 20. 3 plus 12 is 15. 4 plus 9 is 13, but 6 plus 6, both of them being positive, is positive 12. And so we know that this is plus 6x plus 6x, and the greatest common factor across your first row is x. Greatest common factor across your second row is 6, and it is positive because they're both positive. And the greatest common factor in your first column is x. And in your second column is, again, both of them are positive, so it's positive 6. And then when you do your check, x times x is x squared. X times 6 is 6x. 6 times x is 6x, and 6 times 6 is 36. And so we do have the correct pair of factors. So you can still rely on the method that I've already taught you. The only additional thing, if you want to learn something extra, is that if you have something called a perfect square, then you might be able to find your appropriate middle terms much more quickly. And this is just simply the textbook's way of telling you what I just explained about the perfect squares. And for example, this is a perfect square trinomial, as we said, because the square root of x squared is x, so it's a perfect square, and the square root of 36 is 6. And so we know that the first and last term are perfect squares. And so once we know that, the middle term needs to be twice the product of the first and the last. Well, the product of the first and the last is 6 times x. And 2 times 6 times x is plus 12x. And so that's how you know this is a perfect square. And if you want to use that little trick, that's fine. But remember, this is kind of a one-trick pony. It only works if you have perfect squares. And the problem with it is sometimes you won't realize you have the difference of perfect squares because you forget that you need to look for the greatest common factor first. So don't skip that part. So now that we do know that, the way to factor this perfect square trinomial is to take the square root of the first term, which is x, and the square root of your last term, which is 6, and because the middle term is positive, then our plus 6x and plus 6x will give us our required 12x. So if you're going to use this one-trick pony, is this a perfect square trinomial? Well, since the first term's coefficient is 1, yes, x squared is a perfect square. Yes, 100 is a perfect square because the square root of 100 is 10. The square root of x squared is x. And so we have 10x as the product. So this is true, this is true. And the middle term is 20x. And it is positive 20x. And that is equal to 2 times 10x. So yes, this is a perfect square. So we're going to apply the test one more time. Is your first term a perfect square? Yes. 9x squared is equal to 3x times 3x. And the last term, which is 25, is equal to 5 times 5. So, yes. Is the middle term twice the product of the first and the last? Well, the middle term is 20x. The product of the first and the last is 5 for the last term and 3x for the first term, which is 15x, but 2 times 15x is 30x. $20 does not equal 30x, so no, this is not a perfect square trinomial, and the only option we would have to try to factor 9x squared plus 20x plus 25 would be to try to do it by our usual method. Now, the other thing that I want to add in here is that once we know that this is, in fact, not a perfect square, we can proceed to try to factor it using a different method. It may or may not factor, but we can try. So, to this problem, what we're going to do is we're going to apply our usual method. So, first of all, is there a greatest common factor? And the answer is no. And so we will multiply 25 times 9x squared, or actually 25 times 9. And so 9 times 25 is 225, and so we've got a lot of factors. So one thing about it is that we know that there's 1 in 225. It's not even, so we can skip all the even numbers. 3 will divide into 225. And it's 3 times 75. 6 will not, because it's not even. 5 will. 5 will go into 225. 45 times. 7's not going to divide it. 8's not going to divide it. 9's not going to divide it. 10's not going to divide it. In fact, the only thing that is going to divide it are factors of 5. And since we know it's going to be factors of 3 and 5 at this point, we could try 15. And as a matter of fact, its other factor is 15. And because these match, we know there are no more factors. So what happens here is that we look to see if any of these add up to 20. And again, that's positive 20, and both of these are positive. And so this is 226. It doesn't work. This is 78. Nope, that's not 20. This is 50. That's not 20. And this is 30. That's not 20. And so what we have determined here is because none of these work, then what we know now is that 9x squared plus 20x plus 25 does not factor, which is another way of saying it's prime. And this is the really good thing about this method, is not only do you know when something does factor, but you absolutely know when it doesn't factor, because not everything does. Once again, is the first term a perfect square? Yes. 4x squared is equal to 2x times 2x. Is the last term a perfect square? And the fact of the matter is 11 is prime. So, no. Don't even need to bother with that. The answer is no. So here we have one more. Is the first term a perfect square? Yes. It's 5x times 5x. Is the last term a perfect square? Yes. 1 is 1 times 1. The middle term is negative 10x. The product of the first and the last term is 1 times 5x. Which is 5x. And so twice the product of 5x is equal to positive 10x. Is it possible that we could have had a negative 10x? Well, suppose that 1 had been negative 1 times negative 1. Then this means that could have been negative 5x. And 2 times negative 5x is negative 10x. So yes, if you take that the factors of positive 1 were negative 1 times negative 1, yes, this would work, and this is a perfect square trinomial. So yes, even if the middle term is negative, what has to happen is that your last term has to be the product of its two negative factors, so that we still have a positive product, but both the factors are negative. So for this method, this one, we also know now that the factors are 5x and 5x for the first term, and negative 1 and negative 1 for the second term, and that's how that polynomial factors. So is this a perfect square trinomial? Well, 9x squared is 3x times 3x, and 49 is 7 times 7, but again, middle term is negative, so 49 could also be achieved with negative 7 times negative 7. So are the first and the last perfect squares? Yes. Is the middle term, which is negative 42, twice the product of the first and the last? Well, the product of the first and the last is -7 for the last term. And 3x for the first term, which is -21x. And 2 times -21x is -42. So this method would work on, the method of perfect squares would work to factor 9x squared minus 42x plus 49. So at this point, I'm actually going to pause and go back and factor all the ones that we've already determined were and weren't perfect squares. So I'm going to go backwards for a second. We also know at this point that since this did fit all the criteria, that the factorization is 3x and 3x for the first term, and -7 and -7 for the second term. And that does give us the -42x for the middle term. So we're going to look at okay, here we have one that is clearly not perfect squares. And so even though the first term is a perfect square, the last term is not. Therefore, we have to go back to our regular method, which is to first, remember always, step 1, is there a greatest common factor? And since we're looking at 16x squared, -8xy, well, there's common factors there, but this is a y and this is an x squared, so there is no greatest common factor there. So no greatest common factor. So we'll begin the way that we usually begin. 16x squared plus y. Multiply those two together. And since we already know how the x squared plays out, we're going to kind of ignore it and know that we have to have an x in both of these. So what we have left is 16y. And we know the y is going to go in there somewhere, but we don't know where just yet. So we're going to, again, focus on the factors of 16, the number part. Now, 16 is 1 and 16, 2 and 8, 3, oops, 3 didn't work, 4 and 4. We look at our middle term and see that it's negative, but our last term is positive, which tells us that we have to have same signs. And this tells us that both those signs must be negative. So negative, 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 negative. Well, it's pretty quickly evident that this is negative 17, this is negative 10, but this is, in fact, negative 8. We've got to put the y with one of them. So, doesn't really matter. They're both negative 4. We'll put it with one of them. And that means this would have to be negative 4y. And this would just be negative 4. So now we need to look for our greatest common factors in all directions. 16x squared, negative 4xy, well, there's an x in both of them. And 4 goes into 16 4 times. Same thing on the second row. Negative 4x plus y, well, they have nothing in common. And so their greatest common factor is 1. Then we have our first column, and again, we have an x in common to both and a 4 in common to both. And then on this one, the only thing we have in common is the y. Now we've got to figure out signs. So what we're going to do is we're going to start checking. 4x times 4x is 16x squared. No problem. 4x times y is going to give us negative 4xy only if the y is negative. And so we're going to make it negative. And then 1 times 4x will give us negative 4x once again, only if the 1 is negative, because the 4x can't be negative. And then negative 1 times negative y gives us positive y. And so that checks. And that means that this, even though it didn't look anything like what we normally have, this actually does factor. And this method truly does work every time. And so our factors are 4x minus 1 times 4x minus y. Now I'm going to factor this one, and then I'll show you the perfect square part of it. We have 4, 4, and 1, so there is no GCF. And so we're going to put 4m to the 4th in the first box, and plus 1 in the last box. M to the 4th is equal to m squared times m squared. And so we know there's going to be an m squared in both of these. And we know that that has to be because there's an m squared in the middle term. And so what we need now is the product of the first and the last numerical factors, and that would be 4 times 1. And fortunately, 4 does not have all that many factors. There's 1 and 4 and 2 and 2. It's positive, which tells us same signs. The middle term is negative, which tells us that the same signs are both negative signs. This would give us -5, but this gives us -4. And so now we're all the way to the stage of greatest common factor. 4m to the fourth and 2m squared. Well, 2 goes into 4, and m squared is the greatest common factor in both of those. -2 and +1 have nothing in common but 1. 4m squared and -2m squared, well, it has a 2 and m squared in common. And again, -2m squared and 1 has nothing in common but 1. So we do our sign check. 2 times 2 is 4, and m squared times m squared is m to the fourth. 2m squared times 1 will give us -2m squared only if the 1 is negative. And the same thing, 1 times 2m squared will give us -2m squared only if the 1 is negative. And -1 times -1 is indeed +1, and we have our answer. 2m squared minus 1, 2m squared minus 1. Now, if you want to do that by the perfect squares method, then yes, I do realize that this is 2m times 2m, and that this is 1 times 1, but again, then these are both negative. And we have 2m squared for the first term, and -1 and -1 for the second term. And that was a little faster, but again, we had to first do no greatest common factor, and then we had to go through the step of figuring out whether or not it was a perfect square. So since there are very few factors here, I don't know. It's kind of a wash, whichever method you want to use. Here we've got 25x squared plus 50x plus 9. Is there a greatest common factor? These are both divisible by 5, but that's not. So there is no GCF. So we start out, as usual, 25x squared plus 9. We know there's going to be an x here and an x here. And 25 times 9 is 225. And there's a lot of factors of 225, but not as many as you think. Because even though it's 1 and 225, we know that's not the right one. It's not even, so there's no point in trying to divide it by any even number. 3 actually will divide it. And we got 3 times 75. 5 will actually divide it. And we get 45. And then we try 7, and it doesn't work, but 9 does. It's actually 9 times 25. And 11 doesn't work, of course. 13 doesn't work. 15 does. And it's 15 times 15. So, like I said, even though you might think there's a lot of factors, there's not all that many. We've already used 25, so the only other ones you would want to check after that would be numbers that are bigger than 15. But because it's 15 times 15, you've already used 15. When it repeats, you know that you're done. So there are no more factors. So we need to find the ones that add up to 50. And because it's positive and the 50 is positive, we're going to assume that both of these are positive. And it doesn't take too long to home in on the fact that it's 5 plus 45. So even though it was tempting to say it's perfect squares, well, it's not perfect squares because the factors of 25x squared are 5x and 5x, and the perfect square of 9 has a square root of 3. Well, 3 times 5x is 15x, but 2 times 15x is 30x, not 50x. So it didn't fit the perfect square criteria, which is one of the dangers of trying to make things work just because of some shortcut that works once. So here we actually need our original method. And we're going to use our greatest common factors. So between 25x squared and 45x, our greatest common factor is 5x. And between 5x and 9, our greatest common factor is 1. And between 25x squared and 5x, our greatest common factor is 5x. And between 45x and 9, greatest common factor is, in fact, 9. And now we'll do our sign check. 5x times 5x is 25x squared. 5x times positive 9 will give us positive 45. So we're going to assume that's positive. And 1 times 5x is indeed positive 5x, so we're going to make sure that's also positive. And then our last check is positive 1 times positive 9 is in fact positive 9. And so our answer is 5x plus 1 times 5x plus 9. So this one is here as a warning. Don't always assume that the one-trick pony will be your friend. At this point, I'm going to suggest that you pause and take a quick break because we're going to shift gears a little bit. And you've been sitting there for a while, so get up, get a drink of water, walk around, and then come back and finish your notes. Okay, we're talking here about a place where it's actually called the difference of two perfect squares. But rather than show you the perfect square thing right off the bat, let's talk about what's actually going on here. This actually used to be the same kind of trinomial or actually the 4-term polynomial that the others did. The thing is, with this one, this is actually the same as saying x squared plus or minus 0x minus 9. And the 0x comes from two terms that added up to 0. And what we know about things that add up to 0 is that one of them would have had to have been positive, and one of them would have had to have been negative, and that these two numbers would have to be the same, except for the sign. So what we're looking for is we're looking for two factors that basically cancel each other out. So the way that we're going to do this is I'm going to go the usual way. We have a first term and a last term, x squared minus 9. We know that the x squared means there's going to be an x in each of those two boxes. So 1 times negative 9 is equal to negative 9. And that tells us right there that we're going to have one positive and one negative number. We don't know which one's which. It might be the negative is first and the positive's second. But we're going to start listing out our factors, because there's not that many factors of negative 9. Factors are 1 and 9, and 3 and 3. Well, I don't care how you arrange 1 and 9. Positive 1 minus 9, negative 1 plus 9. Neither of those equals 0. However, if you have a negative 3 and a positive 3, that equals 0. And so your greatest common factor method is ready to work. Between x squared and 3x, we have x. Between negative 3x and negative 9, both of those are negative, so there's a negative 3. And between x squared and negative 3x, we have x. And between negative 9 and positive 3, we have 3. And when we do the sign check, x times x is x squared. X times positive 3x would give us positive 3x, so this must be a positive 3x. Negative 3 times x is negative 3x, and negative 3 times positive 3 is negative 9. And so your factors are x plus 3 times x minus 3. This is what is known as the difference of two perfect squares. There is no middle term. We know that it's the difference of two perfect squares because the first one is x times x, and your last term is 3 times 3. And because that last term is negative, we know that one of those is negative and one is positive, and that's what gives us what we're after in getting that middle term to cancel out. This little one-trick pony is worth understanding if you catch on to it. But if you don't, the other method still works. It always will. But again, to reinforce, a binomial is the difference of two perfect squares, or the difference of two squares, if both of the terms, and there's only two, this is only going to work if you only have two terms, if both of the terms are squares and the signs of the terms are different. Okay? Different meaning that this is positive 9x squared minus 25y squared. And in this case, the negative is on the front sign. This could just as easily be written as d to the fourth minus c to the fourth. So it doesn't matter. The thing is, there has to be a difference in the terms and the sign. It has to be a difference indicating a subtraction. And if you can factor the difference of two perfect squares quickly, sometimes it's very efficient to do that. So what you do is you look at the factors of the first term, which is a times a, and the factors of your second term, which is b times b, and you put a in the first place and b in the second place, and the key is that the sign between them is opposite. So I will do the rest of these both ways, but I want to make sure that you understand this one actually is a nice shortcut if you have large coefficients. Is negative. This one is especially helpful because you've got a fraction. And because we've got a fraction, we have to know how to take the square root of a fraction. This is a little bit early to talk about this, but 16 is 4 times 4, and 25 is 5 times 5, and so 16 over 25 is equal to 4 over 5 times 4 over 5. And so that means it's a perfect square. And of course, y squared is y times y. And so using the shortcut method, y is the first term in both of the binomials, and 4 over 5 is the second term, and you just have different signs. The method that I originally showed you doesn't work well with fractions. I'm going to tell you that up front, because finding all the factors of 16 over 25 is much more difficult than you might think it is. So knowing this difference of squares is useful, but you need to understand this part. So if there's anything that I expect to be a little tricky for you in this section, is going to be if you have to deal with fractions. Now the method works very well here, and there are no fractions, thank goodness. We don't have a GCF. I didn't check it in the last one because it was, I hope, fairly obvious there wasn't one, but there's no GCF here either, because the GCF would have to be something common to both 4x squared and 1, and of course that only 1 is 1. So is 4x squared a perfect square? Yes. 2x times 2x. 1 is a perfect square. And so by the perfect square, this is a difference of perfect squares because it's a subtraction. Then we put 2x in the first position in both sets of parentheses, and 1 in the second position, and then put different signs between them. You can still use the other method on this one. 4x squared, negative 1, you know that there's an x in each of these. 4 times negative 1 is equal to negative 4. So you know you're going to have different signs. Your factors of 4 are 1 and 4, 2 and 2. And once we have repeats, we know that we're done. We know the signs are going to be different. Negative 1 plus 4 isn't going to give us 0. Neither is positive 1 minus 4. So we know that one's out. It has to be plus 2 and minus 2. Now that we've got that, we can find our greatest common factors. Greatest common factor there is 2x. Greatest common factor here is 1. Greatest common factor in the first column is 2x. Greatest common factor in your second column is negative, because they're both negative, 1. And because this number times this number has to be negative 1, we're pretty sure that one's going to need to be positive because both of these were positive. So we check. 2x times 2x is 4x squared. 2x times negative 1 is negative 2x. 1 times 2x is positive 2x. And 1 times negative 1 is negative 1. And your two middle terms do indeed cancel out. Either method works just fine. This one we have 36a squared minus 49b squared. First thing you want to check for is greatest common factors, but since this one is even and this one is odd, the only factors of 49 are 7 and 7, and the only factors of 36, besides 1 and 36, are 6 and 6, or several others, but they're all going to be even. So, shortcut method, 36a squared is 6a and 6a. Factors of 49b squared are 7b and 7b because they're both perfect squares. And so in our two sets of parentheses, we'll start out with 6a. And for our second term, we will go with 7b. And put different signs between them. If you do the other method, we have 36a squared and 49b squared, which is negative. And we know that this means there's going to be an A in each box. We know this means there's going to be a B in both boxes. And so what we're worried about is 36 times negative 49. And for 36 times negative 49, I want my calculator, especially to start doing those factors. And that's 1,764. And that's a lot of factors. 1 and 1764. 2 and 882. 3 and 588. 4 and 441. 5 won't work. I'll just tell you that up front because it doesn't end in 5. 6 and 294. 7 and 252. And I'm sure at this point you get the idea that this is going to be kind of slow going. So this would not be something I would ask you on a test unless I was asking you to know how to do this. Eventually what you're going to come down to is the fact that what works is going to be $42. Because 1764 divided by 42, which is the product of 7 times 6, is the combination of factors that it takes. So there'd be a lot of space in between here because there's a lot of other values that will work. So guess and check, or even making an exhaustive list, is not the best when you've got large coefficients like this. When you see a problem on a test or a quiz that has large coefficients, look to see if those coefficients are perfect squares, please. And so this is going to be 42. Oops, change pen. This is going to be 42. This is going to be negative. This is going to be positive, or positive and negative, whichever one you want, because one's going to have to be positive, one's going to have to be negative. Greatest common factor here between 36 and 42 is 6. And because both of them have A's, there's going to be an A. position. And you get the exact same answer in much shorter time. I'm going to leave the last example for you. I want you to use whichever method you feel most comfortable with. And I want you to verify for me that the correct answer here, by whichever method you choose, is 7 minus x squared. Excuse me. Sorry about that. 7 minus x times 7 plus x. And that concludes our lesson.